Okay, so this is Unit 7, Day 1, and we're on the second video now. In this example, we're given a function f at x equals x squared minus 4 all to the exponent 2/3, and we want to find the intervals where f at x is increasing or decreasing. So to do this, we're going to go through these same steps each time. First thing, we need to find the derivative. From the derivative, we're going to find the critical numbers. Those are the points where f prime equals 0 or f prime does not exist. Then, to figure out whether the intervals between those critical numbers are intervals where the function is increasing or decreasing, we're going to analyze the sign of f prime at x in those intervals between the critical numbers. So these are going to be the same steps for each one of this type of questions. As you can see here, I've gone through and found the derivative, just kind of using a simple chain rule. So it's 2/3 times the inside function of x squared minus 4, all to the exponent negative 1/3, and then multiplied by the derivative of the inside function, which is 2x. Simplifying these, go on the top, putting this onto the denominator, and then I've factored that x squared minus 4 so that we're more easily able to identify which the critical numbers will be. So when I'm looking for critical numbers, I do always like to CN, I just use for a short form for critical numbers. I always like to identify what I'm looking for. So this is where f prime at x equals 0 and f prime at x does not exist. So I'm looking for those two categories of values. So looking at my original derivative function, f prime at x equals 0 at x equals 0. So that's when the numerator of the derivative is equal to 0. F prime at x does not exist where there's restrictions on the derivative function. So that would be -2 and +2. So I end up getting 3 critical numbers from those 2 different categories of possible critical numbers. So I'm looking where the derivative is 0 and where it doesn't exist. I'm going to take those critical numbers, and I've kind of set them on a number line so that we can see the different areas here. So we're going to have one segment of this function for everything to the left of -2 on the number line. So from -∞ to -2. So I'm just going to put on these intervals using interval notation. So interval A is from -∞ to -2. Then point B is -2, and we know that that was a restriction on the domain of the derivative. So there's no derivative there. That's where the derivative does not exist. It's not actually a restriction on the domain of the original function, though. So you have to kind of be clear on what you have a restriction of. Then using interval notation, interval C, I'm going to need to test between -2 and 0. We know that the derivative equals 0 at x equals 0. And then the next interval to test is between the critical numbers 0 and 2. And the final interval is between 2 and infinity. So everything greater than +2. So just kind of summarizing, we have points where the derivative, the denominator is 0, which means the derivative is undefined, or the numerator equals 0, which means that the derivative is 0, means the function could be a local maximum or minimum. So this is my preferred way of testing for intervals of increase and decrease. A lot of people prefer test values. When I was in university, we were not allowed to use calculators in any of our first and second year calculus courses. So I got used to doing this. And it's just kind of analyzing the signs of each kind of factor in the derivative. So this is how I'm used to doing it, but you can absolutely use test values, and I will show you that as well. So just kind of looking back at my derivative, I see I've got a 4x in the numerator. I have these two factors in the denominator. The 3, if I'm talking about looking at the sign of the derivative, 3 is not going to affect the sign, nor will this 1/3 exponent. So if we have a negative number in here, the cubed root of a negative will be negative. If we have a positive number in here, the cubed root of a positive will be positive. So that cubed root and the positive 3 out front don't change the sign of the derivative at all. So looking at the 4x, that factor will be negative in these two intervals. So whatever number I pick between negative infinity and -2, or -2 and 0, I'll get a negative there. And then 4x will be positive after that x equals 0 value. If I look at the factor x minus 2, any number in here will give me a negative. If I subtract 2, negative also in here. Any number between 0 and 2, if I subtract 2, that will also be negative. Once I get above 2, subtracting 2 will still give me a positive value. Because I don't actually care about the value of the derivative, just the sign. For x plus 2, this interval will give you a negative for the factor. Between -2 and 0, if you add 2, you're going to get a positive number, and any positive number between 0 and 2 or 2 and infinity, adding 2 will also give you a positive. So then I just look at the signs here. I have 3 negative factors. That means my derivative will be negative. What that means, a negative derivative, about the function, I just draw an arrow going down just to show it decreasing. In the next interval, I have a negative factor, negative and positive. 2 negatives and a positive will give me a positive value. And that, for the derivative, that means that the function is increasing. The next column, positive, negative, positive, gives me a negative. And that means that the function's decreasing. And in the last column, I have 3 positive values. This will give me a positive value for the derivative and show that the function is increasing there. If you don't like this sign analysis method, I prefer it because I think it's actually faster once you get used to using it. You can also use test values, and I've set that up here too. If you do test values, you can just list, like here between negative infinity and -2, I'm going to test -3. And then you'll just take your derivative function, substitute in a -3. But of course, sometimes this is going to be a messy function. It's a lot of typing in on your calculator. But however you choose to do this, I would sub in a -3 and you get a negative value for your f prime. And again, that means decreasing. So it's one of these two tables that you're going to do, not both. And then if you sub in a number between -2 and 0, probably will mostly all pick -1. If you subbed in -1 to your derivative, you get a positive value, and that means increasing. So this looks faster, but there's actually a fair bit of typing into your calculator, substituting in those numbers, and working those out. Between 0 and 2, I would substitute in 1, and I know that will give me a negative value, and it means your function is decreasing, and any number bigger than 2. So you could substitute in 5, doesn't matter. That'll give you a positive value and shows your function is increasing. So really this depends. One of these two tables will be what you will use, and just kind of personal preference, whether you prefer more typing stuff into a calculator and not having to think about the factors so much, versus whether you prefer to be able to just kind of analyze each one and say, oh, I know this will be positive, this will be negative. When you get your final answer here, we see that it's decreasing from -infinity to -2 and 0 to 2, and then increasing from -2 to 0 and 2 to infinity. So I would just add that in, kind of going back to my original function. So I'll just list decreasing and then write that out using the intervals. So it's decreasing from negative infinity to negative 2 and 0 to 2. And then increasing from negative 2 to 0 and 2 to infinity. So this gives you some really good information if you think about all of the graphs that you did in grade 11 and in advanced functions. Being able to find these intervals accurately and know when functions are increasing or decreasing will really help us to be able to do some much more accurate graphs once we combine this together with some of our other information we're going to get from these derivatives.